Welcome everyone to High Performance Computing. My name is Morris and I'm teaching this course together with my colleague Reza, and I will talk a little bit more about it. Today we have our lecture 0, actually the prologue of the course, a slow start if you want, that explains you a little bit why there are so many logos, for instance, here on the slide, and what the content is, and many other questions you probably have around the course. So when we look a little bit into the outline of the course, so what you can expect is that we start after the prologue with the high performance computing introduction, so it gives you a much more detailed introduction than I can provide today. And then we dive already in practicals, as you see here, with practical topics and then more conceptual topics that broaden the understanding. And the idea is really to bring practical topics early for your assignments. So the green ones here are mostly also related to your assignments that you have here. We learn a little bit about parallel programming with MPI and OpenMP. And by this also have to learn a little bit about parallelization fundamentals, which is essentially your first assignment. And normally we would go to much more, let's say, technicalities here, to accelerators maybe and others. But we learned over the last 10 years, of course, a lot about this course, so that we have to give out the practicals early, the assignments. Based on student feedback, we therefore go a little bit different than we would usually go with parallelization fundamentals and other conceptual topics first, but instead you start really with some practical topics. And all of those also usually have here and there some additional lectures, so practical lectures where I will demonstrate, or where Reza will also demonstrate one part, which is then also directly related to your assignment. So when we have clarified the parallelization fundamentals and we can understand how you basically do parallel programming on high performance computing machines, we dive into something which came up the last, let's say, 5 to 10 years more and more, which are accelerators and graphical processing units. I'm sure many of you have heard about GPUs already. And then we also dive directly in the next practical aspect in the course, which is then an understanding of deep learning and distributed deep learning, specifically fueled also with some applications, which we brought in as a new element in the course, given the momentum that really the topic deep learning these days gained in HPC. And there are lots of applications that cannot be done if you don't have HPC resources. So a very interesting topic and a new topic really, hence again also more practical. And then as a special, basically this year and maybe also as the last years, we did CFD as a little bit more of a focus, coming also with the other teacher Reza, that is my postdoc, that we will hear a bit more about it later. But he is really an expert in fluid flow, and he will dive with you basically these conceptual topics called CFD. It's not obvious what that means. It's basically understanding with physics a little bit the fluid flow and so on. And then we will learn quickly also why parallel computing is very important. And there's also software for it, like OpenFoam. And given the momentum that OpenFoam also has, we have also included this in the course, for instance, simulating avalanches in Iceland. Or basically there's also other areas where we work on. Then the idea of having also, of course, a blend of CFD with AI is given also in the momentum these days in HPC. We call that partly also physics-informed deep learning, or deep learning based, on partly physical laws, taking them in, constrained by physics. So this is an interesting new domain where we will learn about deep sequence models, so time series data, and how that reflects in CFD applications. And then also some fundamentals, again, are necessary to understand better what CFD is all about, the Lattice Boltzmann idea, and so on. More recently, also transformer models in deep learning have gained tremendous momentum. We do a lot of research in that area. Hence, we will have also there some practicals for you. As a new topic also, we integrated hyperparameter optimization and AutoML. This is also not obvious what that means to you, but this means largely that many of the HPC benefits, of course, can not only be to speed up the training of these deep learning models, as we will learn, but also to better the models. So the hyperparameters, that choosing them in a very good way is often a big difference between, lower error rates or better accuracy. And we will learn about this in this lecture. And then finally, the green energy is a point that is more and more discussed when we're talking about exascale in HPC applications these days. That, of course, green energy is a topic also to be considered in a course like that. The epilogue is rather a formal close, or if you want, rather informal partly when we go through job description, clarifying your questions, mapping the course material a little bit to job description and see what we teach here is directly relevant to jobs outside. Of course, the second part today will go in all of these different lectures in more detail so that you can understand a bit better what it's about. That's why I want to also continue here. Hence, from the motivation of the course, let us review a little bit high-performance computing as such. Of course, we know that the first lecture will be all about it, and you will understand more, but many of you will understand that it's about these interesting systems. There are racks and a whole hall, basically full of these computing resources. And this is a huge field, right? A field of constant changes. And with this, these days, you can have actually a master in HPC, a specialization. The EuroHPC joint undertaking has a specific project that enables students to take a master in HPC. So hence, what I can teach here in a small course like this is really just the basics and a general understanding of the techniques of HPC and so on. And this is in two facets, really more from the physics perspective, here and there, where we say here CFD is a good example here with car crashes, and basically also how here smoke is actually in a pipe, propagating through time. So these are all often numerical simulation based on known physical laws, and the same is with Earth observation. And here you see also water flow in the groundwater modeling combined with rain in the atmosphere and land surface interactions. So lots of applications that drive the design really of this high performance computing machines that are really heavy in terms of computation, and as such have given rise to the, let's say, whole field of high performance computing in the last decades, really. So hence in the course, you see the red one here. The logo is basically alluding to the airplane flying and being simulated inside the computer. We will learn more about this a little bit later in the course. But you see, we cover with some of the basics here, some elements, but also we'll try to go with you into some domain-specific applications, like the domain of CFD here, but also some others of domain-specific science and engineering. And those are often also fueled by AI these days. Hence, we also change some of the materials really in towards the artificial intelligence. Distributed deep learning with HPC will be a topic, and so on. From programming, it's still sort of a basis. You can program these machines from shared memory and distributed memory. You see that a little bit here. And also this will be explained later a little bit in the course. But still important that you learn these concepts, although we keep this, let's say, to a moderate degree, because in a sense, you have the whole course 1 week, for instance, in Jülich, where you can just learn about MPI, the message passing interface, to do distributed programming on this HPC machines. So in a way, it's a well-blended course based on student feedback, based on news that actually come inside the community. Hence, the logo of the course should be maybe also a little bit updated towards more AI, so we don't do only physics. But the key message to take away is really that you learn about parallel processing, distributed computing. So going away from one GPU, use many GPUs. And with this, we are also in an area where we say we are not anymore scientific computing, what you know maybe from other courses like Maple, MATLAB, Scikit-learn in AI, where you essentially use one laptop or one desktop machine. Here in advanced scientific computing, we really think about the large scale. So computational simulations, physics, but also deep learning, which require much more computing power. And hence we have to stop the serial computing and engage in parallel computing. And of course, this has lots of implications, not only message exchanges that you have seen in the slide before, also technology. So how much memory do I have? How many multi-core and many-core chips I can actually use in my application? And how it can basically use all of these technologies with physical laws, with numerical methods, or with AI tools. So this is something then, of course, where we in this course have also CFD as a special and a little bit of AI if you want, making you ready for the jobs, because they are also screaming more and more for high performance computing and understanding of think big, go in parallel processing. So at the end of the course, you should have really an insight on the latest developments, maybe not everything that high performance can do, especially not if you think about that the domain sciences you see here, from plasma physics up to solid physics, whatever. There are so many of them that we cannot teach that all in one little course. But still, you get the basic understanding how this parallel processing works and how also this high performance computing clusters are built, that networks, interconnects play an important role, and also data intensive workloads we will, of course, tackle when we talk about deep learning and AI. The important concepts we will basically teach you in the beginning of the course, especially with domain decomposition, how I really crunch a big, problem into smaller pieces. This will be an important part when you think about parallel programming. So solving smaller problems jointly together to solve the big problem if you want. And then you will also learn throughout the course, and especially in the practicals alongside the HPC environment tools, which means scheduling, or even compilers when you want to have C programming. Don't worry, we don't do much C programming. It's rather, let's say, a couple of C codes just to understand a little bit on MPI. And then we have AI and Python and so on. And we will also learn that then this parallel computing has different levels where you can target it, especially if you think about using MPI yourself or OpenMP with shared memory. So thinking even about variables in parallel, versus maybe larger tools like TensorFlow, PyTorch at doing AI these days. And again, I think, of course, this is not a course completely on CFD. It's not a course completely on AI. You basically need to take these courses if you are interested in this also, but you know the basics of how to do this in parallel after this course, and also understand the foundations, what you have to think about, for instance, like the domain decomposition we talked about. Hence, you are able to really program HPC systems after this course. And then, of course, take really the advantage of using the scientific computing simulations much more than you maybe know from scikit-learn or MATLAB and smaller, let's say, serial technologies, and to have your grip on the parallel technologies. And of course, those really have a, by design idea of handling the parallelism complexity as well, that we will also learn in the next subsequent lectures. Just a brief point why I should be having the right talking to you about this in HPC. I'm essentially now 20 years in the field, more than 20 years really, having a PhD in computer science from Karlsruhe Institute of Technology in HPC and grid applications. I'm still at the Jülich Supercomputing Center, one of the largest centers for HPC in Europe, and we will talk about this more later. I had there many different positions before I came to the professorship here in Iceland, but it's still a very good collaboration between Iceland and Jülich. So hence my student in the research group, we have around 20 in the research group, going back and forth to Germany and also here. There were many different other elements where I have basically experienced HPC and even also cloud computing in the past a lot at CERN, director and strategic director of EU middleware, for instance, but also being an architect in Exceed, which is the US HPC infrastructure at some point in time. And of course, also then on the data side, I was here and there involved in many different EU projects. So more for this course, a bit relevant, you will hear a term called Europe HPC joint undertaking more often than in the past, because it was more or less recently formed. And I will talk about this in a moment. I'm also the governing board member for Iceland, so also thinking about strategic elements of Euro HPC for Iceland. And again, the university courses you will see on YouTube, many of those in the past, this course material really grown from many different courses like statistical data mining, but also the earlier HPC A and B courses. And like all the years, it will be all, everything open is essentially also available on YouTube if you want. Coming quickly to the Jülich Supercomputing Center, this will come up again and again because we are also using some HPC systems out of this system. Landscape really that is in Jülich. They have many different HPC systems and we make the case for it. Largely speaking, this is a research center that you see here with 5,000, these days probably more than 5,000 people, even under the umbrella of the Helmholtz Alliance that you see here with different centers. Really, some of them are very domain specific, like the GeoFZ, for instance, more for remote sensing and other Earth observation elements. So, but this is, let's say, some of the concrete collaborations we have. And I also told you that we have another lecturer in the course that will take over then when it comes to CFD, to the later parts of the course, when we have the basics and also finish the deep learning introductions. Then essentially Reza here, a postdoc of mine, recently graduated actually at the end of 2024, who is really a computation engineer in this, areas of physics of fluids, fluid flow, and so on, and is an excellent candidate to show you this interesting application area. He will also introduce himself a bit later, so I will also basically continue here to the University of Iceland. I think many of you have probably already read up much of it, otherwise you wouldn't be studying here. But of course, also for a general audience on YouTube, it's quite a important university in the field of remote sensing. So in the higher rankings that we have there, the Times Higher Education and so on, these are all elements where remote sensing is very important for us, but also many other sciences, of course. And we have really many foreign students, Erasmus Mundi, and so on. We are also the coordinator of the Icelandic National Competence Center for HPC and AI under the so-called EuroCC umbrella. So that's a mouthful. So that's a lot. So we have to talk about this because this is now directly also HPC related. Hence, we talk a little bit about the Euro-HPC joint undertaking, which really has a mission to support, the development really of HPC together with the European Commission and the member states of the EU and the, of course, EFTA states like Iceland and Norway and so on, to really have their different projects, different resources available for research, engineering, and also industry. We have a couple of these projects. The EuroCC project is quite important. You will see that on the eHPC website if you want, where our competence center is. There will be also events where you will be invited through the course. We call them workshops, where you can also get some bonus points for the final project. So we're quite active in Iceland in all of these different research projects that you see here. Also in cloud projects. Some of you that took the, let's say, complementary cloud course know that already. The European Open Science Cloud is also something where we're in, but also in other activities of cloud computing. Hence, the Icelandic HPC umbrella of, let's say, these competence centers is something which you see in all the different member states. So there's an NCC Finland, there's an NCC Norway in the Nordics, but also NCC Germany and so on. And we modeled the competencies in so-called simulation and data labs. You see them quite in different topics, from natural language processing, which is essentially something driven by my colleague Hafstein Einarsson, but also different chemistry labs from Hannes Jonsson, computational fluid dynamics, with Reza, that of course is teaching with you, software engineering, Matthias Bog, Helmut Neukirchen, and so on, remote sensing, Professor Gabriel Cavallaro. So everyone who is using HPC in one way or another is really, let's say, part of this competence center, and we structure them a little bit in the simulation data labs to have domain-specific experience to essentially users from industry. You see here two examples also with Methane, the language company in Iceland. We have worked together. We see here a short testimonial, and we actually have developed another EU project called TrustLM with them, and also AI Sweden and others, where we now actually have also language models or large language models for Icelandic trained with HPC resources, and this will be also part of later courses. Or you see more from the physics perspective is Treble here in the acoustic and tactile engineering lab led by Runa Unthorsson here in the engineering department that work together with Treble in this lab to also use HPC systems with the competence center, enabling them much better simulations of acoustics, let's say, for instance, in a classroom, but also in an opera and so on. And we have also here, of course, getting a nice short testimonial. Chances are, if you come to our eHPC workshops that I will, of course, announce in due time, that you meet some people from travel, from Methane, or many other industry collaboration examples. So we have, of course, many different collaborations with many different partners, not only SMEs and industry, also Statistics Iceland. We had a very big event just recently with them. So more talking about public administration organizations that also are part here and there of our National Competence Center activities. So one example I would like to point to you is the Simulation Data Lab Remote Sensing. It's quite large because, as I said to you earlier, remote sensing is quite an important factor for Iceland. There's a lot of deep learning and machine learning models performed in this. And for some of you, it's maybe not obvious what that exactly is. So here you can see with machine learning, you can understand a little bit the Earth's cover, right? So, but we don't do this just with pictures from, let's say, satellites that you see here taken on a daily basis and hours basis, but also basically with hyperspectral and multispectral channels that a bit reaching into the Earth. So this will be also aspects here and there we will give some examples, right? When we want to understand, is it now a building? Is it a river? Is it trees? So this is something where the remote sensing lab is, for instance, working on, for example, and also there we will have some examples out on the course. Coming briefly to the terminology, because I want to make a point that HPC is required these days also for deep learning specifically. So when you not heard about this before, you can see the large world of artificial intelligence, including robotics, is really huge. They mimic human behavior. And it's really a topic that has to be broken into smaller pieces. And one of it is to focus on the area of machine learning, where you're learning from data. So you don't really have, let's say, source code, everything explicitly programmed, but you're rather learning from data. And we will, of course, have course lectures about it, how you do it. And then a specific subfraction of this is what we call today deep learning. So these are actually then neural networks, which are relatively large and have, let's say, specific properties in each of the different layers to make them extremely successful for learning tasks. And one of the learning tasks is, as examples here, classification. So you have two groups of data, for example, a new point is there, and you want to understand, is it, to be classified in this or that group? Or if you don't have any group information, you have maybe distances, like here you have the Euclidean distance, making them a bit closer together than this group. It's something what we call, for instance, clustering of data. And all of these are machine learning data mining algorithms. And some of them are even regression techniques where you want to have certain trends, for example, in the data shown. But all of this will come in different lectures. Just let me briefly give you a video here, which nicely explained the complexity really of new, deep learning models. In machine learning, we did, features, and then the machine learning models like support vector machines, etc., was learned. Here with deep learning, we have also feature learning inside. So the models are much bigger, bolder, have more capabilities. And it's not like that you see here that a deep learning is just deeper in terms of layers and layers. It's not the only thing. Right? So deep learning also has what you see here with convolutional layers, pooling layers, subsampling layers, different logic to do this particular feature learning. And we have a whole lecture about it. But with this deep learning, we have been seeing lots of success, for instance, learning whole faces just from fractions of images, or basically also new innovative approaches with transformer models and so on, what we will also learn in the course. So when you look now the video briefly, what is a neural network? So here we see the classification of digits, right? That you see here, human written characters that you see here on this side. And you use a perceptron learning model, which is essentially one of the earliest machine learning models you can have. They're not particular layers, and we will talk, of course, in one of the lectures about it. But you see now the evolution when we go now to a fully fledged neural network, which is basically based on perceptron, based on the neuron idea that we will talk about, and then maybe make more hidden layers that will come next in the video. So here we can nicely see these layers, right, that you have here, making it a multi-layer perceptron. And if you combine this with backpropagation of error, an algorithm we will talk about briefly, you are actually at artificial neural networks with different hidden layers, making the classification task even more accurate. And this is still not deep learning. It's, let's say, still shallow learning, as we would say, has been there before. And all of these connections you can see here are weights you have to train, you have to learn. And the update process of this learning is quite computational expensive. Hence, more and more HPC is needed. And we will also make the case that GPUs are just beautiful for this. I think here you can see nicely now the difference. So convolutional neural networks is in the realm of deep learning networks already. And you see also, instead of the previous one that you have seen putting more hidden layers, hidden layers, hidden layers, that is not where deep learning really points. So you see nicely here with the character, the different feature maps that are actually built. You know, the convolution process, having then also, you know, different layers here to carve out features really of the digits. So small round, small element parts during the subsequent, let's say, layers that you have there. At the end, you have still a fully connected network that you have seen before for the decision making that actually performs in the classification task. But many of the deep learning elements that you will see in the course will have the property to also learning features. And that's where they're really good in. So spiking neural networks is something that we don't really focus in the course on. It is more, let's say, an advanced topic in machine learning. So I would like to stop here. Coming back to the idea why we need HPC. So you talk about a lot, Morris, about machine learning, deep learning, bring that all on one slide. And what is the data aspect, all of that? And well, what is the, you know, model performance accuracy we are all interested in? So this was sort of a question I got when I have to talk in the Deutsche Bundestag, the German federal parliament, where they said to me rather, you know, for politicians, you have to make that on one slide. Okay, so not long slides, just explain everything in one slide, bring everything together. And I think that's what I got good feedback in, is essentially this slide, and hopes to understand the basically point of combining all of these terms, if you want. So you have seen dataset volume is a key element in machine learning and deep learning. The more big data you have, the more realistic it is to do deep learning and so on. But you will also see serial limitations. So when you use, let's say, statistical computing with R, scikit-learn, Weka, MATLAB, Octave, at some point in time, they will not be able to do this anymore with, let's say, traditional classifiers like SVMs, random forests. There are parallel SVMs that we also research. But essentially talking that when you have more and more big data, your small laptop will become the key limitation. So you need something what we call high performance computing and cloud computing. The more you go to the new networks we have seen, small neural networks already can benefit from the amount of GPUs we have in high performance computers today. But if you then really go to medium and large deep learning networks, large transformer models, large language models, and others, then you see the footprint of the training time for those will be significant. And this is not what you can do in a laptop anymore in a sensible way. So hence here, high performance computing is really needed. And we will make the case with GPUs, particularly why is that so successful. It enables me also to say that, of course, these deep learning networks have now surpassed the accuracy and performance we had in previous computer vision algorithms and smaller approaches or traditional learning models if you have larger data sets. So if the data volume is still small, and that's also important to understand, random forests and SVMs are maybe still better than deep learning. So the ordering that you see here is not valid in the first part when we don't have enough data, because deep learning and HPC really need lots of big data sets. Right, and with this, the important differentiation also from high performance computing and high throughput computing. Some of you know that already from the cloud course. It was much more high throughput computing. Here we talk about large machines, really well interconnected together. This is something we talk about and what we see as a major difference between those machines. And that makes them also very costly, because essentially this, cables that you see a little bit when we put here in the upgrade of this machine is the most expensive factor to date, together with the GPUs. And here you see some interesting idea of flops, so floating point operations per 1 second. What is a bit a metric, how quickly you can actually, essentially can compute these things. And then you essentially have also the idea here of the Joule supercomputer and the Uqueen. These are all systems which came a little bit, up to the idea over the last, let's say, 10 years. And you see here now with Joules, one of the cutting edge machines, 936 compute nodes with lots of CPUs and GPUs. Here overall 3,700 GPUs. And then we will talk about a modular computation concept later on. Just a couple of things before we close about the Canvas tool, the office hours, and so on. Please send to my assistant. You see the email here. Any requests for office hours. Everything else will be really on Canvas, except I think final grades are done via UGLA. And all of that will be basically published around this. From the overall course organization, we have 3 assignments, which make 40% of your grade. Plus, of course, then there will be a course project with 10 to 50% of your grade. So the assignments we already talked about in the beginning, the practical lectures will be quite related to it. For the assignments and the course project, it would be important to form groups of 2 to 3 people and also send them please to me and my assistant. The course project will be 50% of your grades, or a major part. Hence, essentially, we have a report in April and start with this in February. But there will be a midterm report necessary, which gives you additionally 10% grade if you start early, because many of the students always start the final project more or less very, very final, and we want to try to work around it. There will be also invited lectures throughout the course, and for the knowledge, the yellow blocks really captures a key essence that we have in each of the different slides. For question and answers, we have usually and also, of course, Canvas can be used for commenting. Again, also the grading, submissions of your assignments, all will be done on Canvas. And with this, I would like to just point you also that, of course, in YouTube, you will find the recordings of the previous courses. So if you're interested, from the beginning today, I changed here and there some topics given, of course, the more important these days, like hyperparameter optimization, for examples. But the old lectures are also there, and the new high performance computing course will be also, of course, be available for you there. We also are very active in social media. It's very important for our EU projects, for funding. No one wants websites anymore. Everybody is looking on social media. So there's also possibility to engage with our community there. If you want, we're on LinkedIn and many other platforms. Finally, an anticipated question. So associated literature, bibliography is usually something where we have this in each of the different lectures. So in this sense, you see here already that the bibliography also in this would be something to look at. If you want to know more about a book, for instance, here, Georg Hader or so, this might be an interesting book to look at. And also the courses you have on YouTube, you see we have here got extremely good feedback all over the years for the lectures, putting them on YouTube from the YouTube community, far beyond the Icelandic university. And in every lecture, I will give you a video to look at home. And here we start with the course with a prologue today. I would encourage you to look at this YouTube video from Praise before we start then the next part 2 about the detailed course outline and content together with Reza. So see you very soon.